Thanks, Megan. My name is Adam and I am the researcher for this project. Industrialised countries typically have major water treatment facilities and supply water to residents via a network of piping. Developing countries such as Nepal, however, typically have decentralised water systems where residents may need to travel distances to source unfiltered water from wells, streams and natural springs. To address water filtration and disinfection requirements, centralised upstream processes must be made affordably available for residents in their home or at the source of water. Point-of-use systems address these requirements and are already found in the homes of developing countries. Key elements to the success of a point-of-use system in a developing country include initial outlay and ongoing costs. The system must be economically viable. Sustainability. Are the resources required to operate and maintain the system available to the community? Is the system robust and able to provide prolonged service with minimal downtime? And is the community willing to commit to the system's ongoing use? Possible effects on the environment. Are there chemicals required or a byproduct produced that may impact the environment? And to operate the system, does it put added pressure on strained resources such as fuel for cooking or electricity? And finally, is the system appropriate and acceptable to the community? Is extra labour required to operate and maintain the system, given the day for some members of the community is already a labour-intensive day? And will the community understand the concept and accept the need for such a water filtration system? One point-of-use system that meets these key elements is clay pot water filters. The pots are small, easy to use and designed to be used at a household level and will produce a sufficient amount of potable water within 24 hours to supply a household, producing approximately 1.5 to 2.5 litres per hour. Economically, clay pots can be purchased at a very affordable price, or if the correct materials are available, communities may be able to make their own. They work by allowing water to slowly seep through the base of the pot. The mechanism of filtration is determined by the porosity of the medium used to build the filter, as variations of pore size alter the process and speed at which filtration can occur. Clay pots impregnated with silver or copper, for example, have shown that the level of contaminant removal is further enhanced. Another point-of-use system is the use of solar energy for disinfection. Solar disinfection, or SODIS, has been utilised in many developing countries as a point-of-use system because it is free and easy to source materials. The amount of water that can be disinfected is only limited by the number of plastic bottles available. SODIS is simply achieved by filling PET plastic bottles, shaking to oxygenate the water, and then simply placed under the sun anywhere from 6 hours to 2 days. SODIS utilises ultraviolet radiation, which kills bacteria, viruses and parasites. Warmer water does speed up the process. Another use of solar for disinfecting is solar pasteurisation. Once again, solar pasteurisation is affordable, effective disinfection that is simple to use and offers the ability to build your own. Solar pasteurisation, unlike SODIS, which uses the sun's ultraviolet rays, uses heat from the sun. Pasteurisation is a concept that has been widely accepted for purifying milk and other products, but not so common for water treatment. Typically, a vessel of water is contained within a reflective compartment to maximise heating. Lab results have shown 99% of microbiological contaminants cannot survive in water heated to 65 degrees Celsius for 1 minute. The amount of produced clean water is dependent on vessel size. While some health organisations in the past have encouraged users to boil water to ensure purity, most protozoa and bacteria are inactivated at much lower temperatures. Boiling water is generally recommended to disinfect, but in actual fact it is excessive, particularly for environments where access to fuel is limited. So if these methods are currently available, why are they not already being utilised? Clay pot filtering is only truly effective with metal impregnation. They can also crack and break, and in order to replace they may have to be sourced from another country. SODIS is time-consuming. Communities lose interest due to the long process of cleaning, filling and handling plastic bottles. Bottles are not cleaned sufficiently, the system lacks ownership or pride, and overcast days can increase time required. Solar pasteurisation requires materials not always available. The concept is not completely recognised. The general belief is that water must be boiled to be safe. The systems are not typically robust and cool weather decreases efficiency. So why combine all three systems? Due to their shortcomings, they are not necessarily reliable or effective individually. Combined under ideal conditions, the combination of three systems provides an extremely efficient filtering and disinfection system. Each system assists in eliminating the deficiencies of the other. How to combine three systems in one then? All components are contained within a robust manoeuvrable steel container, a 44-gallon drum. Fine mesh provides initial filtering to remove larger particles when filling the first stage. First stage of filtering and disinfection is via a clay pot filter, providing initial fine particle filtering and removal of microbiological contaminants. The second stage of disinfection is provided by clear tubing circled around the drum, providing the benefits of UV disinfection as found with sodas. The tubing is contained within a reflective back and wings to heat the water inside the tubing to further disinfect, a similar process found in solar pasteurisation. So what are the benefits of our design with the three methods combined? It makes for a robust and suitable design. The 44-gallon drum makes for a sturdy construction and rigid frame and helps protect the clay pot from damage. The system is still manoeuvrable to maximise efficiency, and it provides sufficient potable water for a household, approximately 10 to 12 litres per day. It is technically proven, as all three systems have been subject to significant research separately and have demonstrated their ability to remove microbiological contaminants. Combined, it is economically sound, and as shown, there is minimal to no outlay required for all the components. Materials are relatively easy to source. The system is environmentally responsible, as it does not add any extra strain to resources and no hazardous byproducts are produced. And lastly, it is culturally acceptable. The system encourages ownership, interest and pride, as the system commands significance due to the satisfying level of construction and complexity. The need for water filtration is already understood, so the system should be welcomed.